Good morning, welcome to the CABE webinar for Wednesday the 21st of October. Today we're looking at Cordek Solutions CPD with Simon Roberts. My name's Jordan and I'm the Regional and Student Services Coordinator here at CABE and I'll be your moderator this morning. As you know, we like to make these as interactive as possible, so please do send in any questions or comments that you have. You can do this via the questions tab appearing on your screen. If you're watching on YouTube, you can email us using the email address webinars@cbld.com, or you can tweet us using the hashtag CABECPD. So this morning, your presenter is Simon Roberts, who is the Technical Advisor at Cordek. Having spent the last 35 years in the construction industry, the last 12 of which have been with Cordek, Simon has attained a wealth of technical knowledge regarding subjects related to ground heave, ground gas protection, structural fill and formwork applications. In his role at Cordek, he represents the company in East Anglia, South Midlands, the Northern Home Counties and North London regions, providing support to contractors, designers and specifiers alike. In addition, he is particularly passionate about the role professional development plays in the development of individuals from the construction sector. So if you give me just a couple of seconds, I'm going to hand over to Simon and he'll take you through his presentation.
Good morning, everybody, and welcome to the Cordek Solutions CPD. And thank you very much indeed, Jordan, for the introduction there. Okay, so today we're going to be looking at ground heave solutions, VOC and ground gas protection, structural fill solutions. And the CPD is really an overview of those three main areas that Cordek work with. We also have a range of void formers, permanent formwork for ground beams and pile caps, formwork for ribbed concrete floors, and that covers our trough and waffle mold products, a range of piling products, temporary protection products, complex formwork for in situ concrete, and that really comes under our CNC routing technology to produce the complex formwork for those in situ concrete applications, patterns and molds for precast concrete and GRC. That takes us through materials that we use such as GRP, Recley, and the production of patterns and molds for that particular application. And we also have a range of non-construction applications and products that we take to the industry. So Cordek as a manufacturer are predominantly involved in the construction industry. However, we do cover the sectors of leisure, marine, automotive, rail, highways and landscaping. And indeed, in any one of those sectors, you may come across the need to introduce a polystyrene product to form a solution or some gas protection measures. So we're going to start off with looking at ground heave or ground movement. And principally, this occurs in two different areas. So if we consider, first of all, the slide on the left-hand side there, the residential application, you'll note that we have a crack extending up through the external envelope of the brickwork of the building. Now that crack has been caused by a volume change from the strata below, and that upward force has come up through either our slab, our beam or our pile cap and given us the resulting cracking in that external envelope. That situation will also cause compression of surfaces underneath the footprint of the building, and heave can occur from three main areas, either as a result of a potential volume change from an expansive clay soil, or from reconstituted slag, which is a byproduct of the mining industry, or the freeze cycle. And the freeze cycle really is where we're looking at areas of permanently frozen strata that may thaw or freeze, and it's that thawing and freezing cycle that is replicating what a clay soil does when it expands under heave. The right-hand slide there, the commercial slide, is a bit of an extreme version of what we would consider overburden recovery. So that shaft is the Moorgate shaft on the Crossrail line and going through London. And even at that depth of 40 to 60 meters, after we'd removed that mass bulk of soil, we were experiencing a potential volume change from the strata below. So in that particular instance, we introduced a cast in situ suspended slab and a specially produced Cordek product to accommodate that amount of movement at that depth. Moreover, you will probably see that in areas, and certainly around London, where there are properties with basements, and during basement construction, overburden recovery, where we are removing that mass bulk of soil, that would be a similar application to what you see in the commercial slide there. Throughout the industry, Cordek deal with various warranty providers, Premier Guarantee, Keydis, NHBC, and NHBC produce a range of documents, technical extra and standards. This one covered the common causes of heave related damage, which was quite interesting. So incorrect foundation depth, well, that can be remedied by consulting 4.4, building in expansive clay soils, and selecting your correct foundation depth for your application. Lack of heave protection, so that is where you people very kindly specify our products, and the contractor or the project then deems that they don't want to actually put those products into the build. Poorly installed heave protection, that's more where we can assist as a manufacturer with advising contractors and engineers and architects as to the best method to actually install heave protection. And that covers things like the introduction of a blinding layer or taping joints at formwork to stop the ingress of concrete slurry weeping down into the area where we're looking to procure a void. So how do we know if we've got heave? Obviously, we would undertake site investigation. That can be done by either a specialist geotechnical site investigation company. Now, that may be a standalone company, or for some of the larger structural consultancies, that could be an in-house operation, one of the services that is provided by those particular people. So we go to site, we identify the soil strata, so physically what is there, the characteristics of that soil, how it's likely to behave, and from that we get the plasticity. We understand that's the plasticity index, and we can also identify the heave potential, so that would put it into a low, a medium, a high, or an extra high potential volume change. And it is the plasticity index that we consider when we are looking to specify the depth of a compressible polystyrene void former. The other way of actually finding out if we've got heave, if we don't want to have a specialist geotechnical site investigation undertaken, we can refer to historical information. That can be provided either by the NHBC or the local building control, or perhaps even just simply consulting the geology map of the UK and understanding where expansive clay soils occur. As with everything, there are supporting industry guidance documents. So we've got building regs, we've got chapter 4.2, which is, as we all know, a very comprehensive document, which is building in expansive clay soils near trees. It is a NHBC generated document. There's also the NHBC free app, which is more of a mobile thing. You can update that or upload that, sorry, onto your tablet or your smartphone or your PC, and that really gives an overview of everything from the foundation right the way up to the roof. And I understand it is a free download from the NHBC. In terms of how the industry actually deals with the problem, if we consider the first slide on the left hand side there, we could in theory remove the expansive soil from site, thereby alleviating the problem. We would obviously have to replace that expansive soil with something, and it's usually in the form of made ground. It has happened twice in my particular experience at my time at Cordek. Both times in Milton Keynes, the contractor did remove a large area of expansive soil and re-imported made ground. Unfortunately, it didn't alleviate the problem completely, and we still had to introduce anti-heave protection measures for that particular building. The other way of dealing with it is perhaps to look at soil stabilization. That's the introduction of lime sulfates into the soil, where we modify the actual characteristics of the soil that is on site. With this particular application, it does have its plus points, so you could alleviate the need for piling. There are also some negative points to it as well. You have the introduction of men and machinery on site, which is quite a time-consuming process to undertake that lime stabilization. You would also have to modify the characteristics of the whole site rather than the actual footprint of the building that you're looking to actually introduce. And there is also some post-monitoring work that has to be undertaken to make sure that lime stabilization has occurred correctly and the strata has been modified accordingly and is staying modified. Then we move on really to what we can provide in terms of a polystyrene void former. The left-hand slide covers the block and beam scenario, predominantly a housing scenario. You can see there we have our block and beam floor. Underneath our block and beam floor we have a voided area, and that gives us somewhere for the strata to actually move into should heave occur. We do, however, have to consider heave protection at the perimeter and any potential volume change higher than a low situation. So for a medium, a high, or extra high, we would have to introduce lateral heave protection around the perimeter on the inside face of that particular perimeter foundation. The right-hand slide covers the heave protection product, the void former that Cordek would offer you. It is a compressible polystyrene void former. It's only designed to be used in conjunction with a cast in situ suspended slab that is either tied into a piled and ring beam foundation situation or tied into a deep trench fill foundation situation. You can also use it in a piled raft situation. It is not suitable for ground bearing slabs. The reason for this, if we can see there, if we can see there on the right hand side there, the heave protection product, the void former, it's for use with a cast in situ suspended slab. The reason for that is we have to resist the upward force generated from the strata below in order to get those polystyrene legs to progressively collapse. So what we're considering here is that we are introducing a type of formwork that is protecting our slab, our beam, or our pile cap whilst that concrete goes off and maintains full strength. Once that concrete has gone off and maintained full strength, and the slab or the beam is essentially spanning, you have subsequent heave, you do have that voided area underneath your concrete for that strata to move into. So moving on to the actual Cordek solution, we have a range of products called Cellcore HX. These are a 4th generation product, 25 years in development, and they have full BBA certification. And the Cellcore HX range is an umbrella term that covers 3 products within that range. We have HXS for slabs, we have HX Plus for providing heave protection and insulation under slabs, and we have HXB for beams and pile caps. The product range itself will take you up to 900 millimeters head of concrete. So that's physically how much concrete you can put on top of the actual product. If you want to protect concrete depths from 900 up to just under 2 meters head of concrete, then we would look at a different range, which is our Cellcore HG range. Now the Cellcore HX range, the components of it are all pretty much the same. So you have a molded cellular leg with a range of different tops glued on top of those molded cellular legs. There are also drainage holes in the legs, which enables the product to be used in areas either where you have a high water table or in a coastal environment. So this one we can see here is our HXS product. It's a standard product for use under reinforced floor slabs. It comes in a 1.2 by 2.4 meter panel size and is made up of a collection of cellular legs, as I've mentioned before, with a 10mm twin fluted polypropylene top, which is strong enough to actually walk on during placement of base spacers and reinforcement. You can see there that the actual product is sited on a blinding layer. We do like to see the product sited on a blinding layer for various reasons. First of all, we want to start off with a flat level surface to minimize wastage of concrete pour above. Secondly, we like to alleviate the product coming into contact with large aggregate on the strata's surface, so hence the blinding layer, and compacted blinding as well, because we don't want the blinding layer to actually go up into the cells of the product and detract from its performance during heave. So basically, we would introduce a 50mm blinding layer. You've got various options available. You can either have concrete, ling mix concrete, a sharp sand and cement dusting to form a crust. If it's an internal application, sharp sand. You can also use 10mm pea shingle. However, building sand isn't suitable. Building sand is great when it's wet, it's nice and compacted. However, when it dries out, it becomes fluffy and will actually fill up the legs of the cells underneath the product. So the HXS product is just a standard product. It provides no insulation value whatsoever for underneath the actual floor slab. If you are considering insulating your building, then you should consider looking at this product, which is Cellcore HX Plus. So this is a combination product. It has a range of cellular legs with different depths of insulation glued onto the top of those cellular legs, dependent upon the target U value that you need to hit. And again, we have the protection board on top of it. You can see that the operative in the picture is actually introducing formwork tape at the joints. That is to stop the ingress of concrete slurry weeping down between the panels and causing a dead spot. In this particular application, we had formwork tape, then the slab was poured, and then the damp-proof membrane was on top of the slab and underneath the screed. Usually in most site applications, you'll find that you just roll out the DPM above those particular Cellcore panels and away you go. Either function will stop that ingress of concrete slurry weeping down in between the legs. So in terms of the U-value calculation service, we can offer you a U-value calculation service. It's a free of charge service, and we would ask certain questions. So the area of the actual slab, the perimeter, linear meters, the target U value that you would like your building to achieve, or your slab to achieve, and the thickness of concrete poured on top, and the amount of potential heave. And from that, we can specify a product for you. We can put all of that into a U-value calculator, and it will outline the depth of insulation required to hit the target U value. Now, those questions are normally ones that we would ask if the slab is at ground level. If the slab is a basement slab, we would then go on to ask, is the basement occupied or unoccupied, heated or unheated, and what is the makeup of the wall, and what are the actual finishes that are proposed for on top of the slab. And from that, we can pinpoint and give you a very much more accurate U-value calculation. The next product really is a bit of a link here between what we are looking to introduce in terms of lateral heave protection, as well as our Cellcore product for protecting the beams and pile caps introduced on site. So what you see there is Cellcore HXB. We manufacture that in a 2.4 meter length, and it's manufactured to beam width. And that way we can ensure that the legs coincide with where the top of the formwork meets, and we don't experience any of the legs breaking off and the product overturning in the bottom of the trench. It has a 5mm board on top of it rather than the 10mm board that I referred to earlier on for the HXS product. The reason for that is we're not actually anticipating anybody walking on the product during installation. So the trench is excavated, we introduce our blinding layer, we then introduce our Cellcore, and on top of that we would then put our base spacers, side spacers, reinforcement cage, wire our formwork together, pour the concrete, backfill, and away we go. HXB can be used for pile caps. What I would say though is if you have a close proximity of piles together, either 3 of these circular piles or 4 of these circular piles together, and you have a pile cap that is linking them all together, it might be considered actually quite a small space, and we might have site personnel trampling backwards and forwards over that small space, introducing quite onerous rebar. If that's the case, then there are a couple of ways to alleviate that situation. We can either change the specification to an HXS product, which will give you the 10mm top, more rigidity, or we can introduce a 50mm blinding layer on top of the actual product, again to protect that cell core underneath. The green product that you can see there in the picture, so this down the side here is Heave Guard for lateral heave protection. It replaces our Claymaster product. It has exactly the same range of thicknesses, NHBC, BRE recommendations. It's all exactly the same method of manufacture. It's now a green color rather than the pink color, which was the Claymaster. So if you were familiar with Claymaster and you would like to specify Heave Guard, it's the green one, please. And also we have our pile collar that you can see there. Now that basically just introduces a nice connection between the edge of where our pile is and our actual run of cell core that's coming in there. So we normally manufacture the pile collars to beam width, to the same depth as the actual anticipated heave of the cell core, and we can introduce them with either a circular hole, a square hole, or we can offer you a hot wire cutter for site fabrication should the piles be offset. As you can see, it's set up there. Obviously, there is no formwork. As I mentioned in one of the first slides, we do have a range of different formwork solutions that we can offer the contractor. So what you see here is an example of our cell form HX system. So we have a U-shaped profile. It's an 8mm formwork, plastic formwork, that is glued on top of our run of cell core, which is our HXB. Again, 2.4 m run, cut to manufacture to beam width. So the idea behind this cell form HX system, that it is a complete system. It comes with straight line connectors, form braces, corner pieces, external corner pieces, infill panels, heave guard, and the pile collars. So really, when your contractor has a set of drawings, accurate site dimension drawings, we can manufacture our cell form system to fit those drawings. So when it goes to site, it's like a big boy's jigsaw, put it all together, put it in the trench, and there's no on-site fabrication required. If your contractor doesn't want to choose this particular system, but would like to just introduce the cell core down below and perhaps use just loose sheets at the side there, introduced at the side, and we can also offer the actual formwork loose, and we can sell you that in conjunction with the formwork tape, just to take those joints down the side there and along here to stop the ingress of slurry, as I mentioned before, weeping down into this area where we're looking to procure the void. So we predominantly have the plastic 8mm formwork. We also can offer the steel formwork, which is similar to the Peckerfield type of product, which is our steel frame with our polythene wrapped over the top of it. So there is a range of formwork available to you. Just going to look at a little bit now on specifying the actual product itself. So essentially, it is a very simple product to specify. We only really consider two things: the actual depth of product, and that is in line with the amount of anticipated heave, and we then look at the grade of product, and that's in line with how much concrete we're putting on top of it. So if we think back to our site investigation, we've got our plasticity index there. We've also got the potential for the product to heave, low, medium or high. We then can see our void dimensions required here, and these are the various depths of products that we would introduce underneath either our slabs or our beams. So essentially, if you look at this one here for a low potential volume change, if you were putting it under a beam, we would have an 80mm leg with a 5mm top. Under a slab, an 80mm leg with a 10mm top. In terms of selection of grades. It's all determined by the amount of concrete that we're anticipating putting on top of the actual product. So each grade has a color code, and those color codes are put on the product when it goes out to site. So the contractor is able to select and easily find which grade goes in which area. So you know, if he's got a slab that's up to 220 millimeters, he's going to put everything red underneath that slab. If his beams are up to, let's say, 450 millimeters, everything yellow is going to go under his beams. So it does make life a bit easier for him. Each product has a safe load and a failure load. So in the example of this one here, Cellcore 710 grade, it has a safe load of 7 kilonewtons per square meter. So it will support 7 kilonewtons per square meter. Okay, it's fully failed or compressed at 10 kilonewtons per square meter of upward force, and the maximum concrete depth 220 millimeters. As I'm moving through all of this, all of the facts and figures that you're seeing in this presentation are actually outlined on the website. So if there's anything you're unsure about, if you go on there, select your product, select your data sheet, this information will be contained within those data sheets. So this is just a design example for a lightweight slab. So basically we've had our site investigation, we've identified that we've got a low potential volume soil, plasticity index of 15. So in our selector table, that's coming in there. You can see in between 10 and 20, we've got a 15 there on the plasticity index, low potential volume change, 50 millimeter void required. So therefore, under the slab, 90 millimeter HXS for slabs. Okay. So we would do our little engineering calculation there to determine our total load that's going to be put on the product there. So we've got, that comes out at 7 kilonewtons per square meter. And so that enables us then to actually select our particular grade. So for up to 220 millimeters head of concrete, grade 710. Okay. So with everything, we have a full specification at the end of it. So Cellcore tells us what the product is. 90 millimeter gives us the depth, so we know it's for a low potential volume change. HX gives us the range. S denotes it's for slabs, and 710 is the grade. So our safe working load of 7 kilonewtons per square meter, fully failed at 10 kilonewtons per square meter of upward force. That concludes the section on ground movement. We're now going to move on to VOC and ground gases. So sources of VOCs and ground gases. The left-hand slide there you can see naturally occurring. So that we would consider as our greenfield sites. So for example, we might have degradation of vegetative material. The picture you can see there is a peat bog. So, you know, generation of methane gas, perhaps from that sort of scenario, or where the areas of naturally occurring strata produce things like radon gas. Moreover, we are looking at the right-hand slide, which is the man-made slide, the activity, any activity undertaken by man that would encompass an industrial process that uses various contaminants that might leave residues of those contaminants on site. And that's predominantly our brownfield sites. So a lot of industrial processes that have been going on. Perhaps there may be naturally occurring gases and contaminants there in conjunction with ones that we've introduced. So that particular slide there, you can see we've got an old disused factory unit. In theory, if we wanted to, we could actually convert that and introduce gas protection measures to adequately protect that. Moreover, though, I would suggest that that would be demolished and a new build would be introduced on that particular area. So typical ground gases and contaminants. So we have the big three, methane, carbon dioxide and radon, a range of other contaminants, VOCs and hydrocarbons. So basically the point about the fag smoke on the slide there on the left hand side is that you actually can't see these gases unless they're in a particular concentration in a confined area, very often you can't smell them until they reach levels that could become harmful. So they are very real contaminants and gases that should be considered in a build where we need to protect the occupants of that building from them ingressing into the habitable space within that building. It's all about risk and removing the element of risk. So basically this is our Venn diagram that shows us the source. So the source is where the actual nasty is. The receptor is where we are, or livestock contained within our proposed building. And the pathway enables that source to actually migrate to the receptor, therefore introducing an element of risk. If we remove the pathway, so a pathway intervention type of system, a passive gas ventilation type of system, then we remove the element of risk from that source transferring through to the receptor. If we think back to our expansive clay soil, we undertook a site investigation for that particular application, and similar things are undertaken for a contaminated land area. So for example, we would go to site, we would introduce a range of boreholes, usually 6 over the area of the site, and they would be installed over a period of time that is designed to cover various different seasons and various different weather activity. From that, we can then establish what is physically there on that site, the concentration of what is there on that site, and the flow rates in litres per hour it's coming out of the ground. From that, a gas screening value calculation is done, which will put the site into a level of severity, 1 being the least severe and 6 being the most severe. This particular slide here just shows you examples of conceptual models. So some of the common ones are landfill. So landfill would be the source, the elevated water table and the permeable strata above would be the pathway, and the receptor would either be the people living in the houses with or without basements and the people working in the actual petrol station. The petrol station is another interesting one. So obviously the petrol station could be the receptor there. The petrol station could also be the source. So what we're seeing currently in developments is a lot of petrol stations that are being decommissioned and residential projects and schemes are being introduced on the footprint where the actual petrol station was. So there may be residual hydrocarbons or nasties in the strata there left over from the actual petrol station, for example, petrol, diesel, oil that's seeped into the strata below. And if we're introducing polystyrene into the build, or if we're introducing gas protection into the build, then obviously we would need to consider that before we start our project. Again, there are various ways of actually dealing with the problem. So these 2 slides cover source removal and soil remediation. So essentially in source removal, we are removing a level of strata that is deemed to be contaminated and re-importing a clean level of strata that isn't. Now that again does have plus and minus points. You can certainly, if it's a residential application, you can certainly be quite safe cutting your grass and growing flowers. You might not be so safe if you are actually going to grow produce in your back garden and then eat that produce. So as I say, it does have its limitations. It's usually to a depth of about 600 millimeters that is removed and then re-imported. The right hand slide is soil remediation. So that is where we actually clean the soil itself. Again, it does have its downside. We could introduce bacteria into the actual soil that we're cleaning, thereby making it worse than when we started. Again, you can see there's a lot of machinery needed on site to undertake that particular process, a lot of labour needed to undertake that process. So again, perhaps a time-consuming application. In terms of the Olympic Park down at Stratford, when the Olympics were going on, all three methods that we see were used in that particular project. So they used source removal, they used soil remediation, and they also used the pathway intervention method. So what we can see here is our vent form system, and there are three main components to the system. So if we look initially at the vent form panels, these panels here are sited underneath the actual soffit of the slab, and you can see there underneath the panel there is a void, and that void is maintained and kept open. The idea being that the contaminant migrates up through the strata below into this area underneath where the actual slab is, and is diluted and dispersed by tidal air out of the building, out to atmosphere. What we're looking for in terms of guidance is one complete volume change of air every 24 hours underneath the footprint of the building, and where practicable we should be ventilating to atmosphere on all four sides of the building. Where that isn't practicable, if we can just ventilate on the two longest sides of the building and introduce a cross-flow situation. So those are the vent form panels, and we'll come on to have a look at those later on. The second part of the system would be a membrane that is installed above the top of the actual vent form panels. Now, in terms of guidance, the membrane should be a continuous impermeable layer extending over the entire footprint of the building, going across the cavity and terminating at the external leaf of the building, where it can be trimmed and it can be visually inspected. So if you have any penetrations going up through the building, they have obviously got to be sealed. If you have any walls going through the building, adequate sealing around there. Lift pits, again, all sealed. At the perimeter, which is the last piece of the puzzle, we have various venting outlets to atmosphere, and it does depend on what type of envelope of building that you have as to what type of venting medium you would select for ventilating your gases out to atmosphere. And we'll look at those as we move on through the presentation. There are industry guidance documents, supporting documents. They're all good bedtime reading. They are quite contaminant specific. Some of them are quite new and up to date and are being constantly changed. BRE report 211, for example, is a good one. DOE Partners in Technology Guide is quite an old one. It considers ventilating mediums for under a slab, and it considers using a metre wide strip. So that is how the information was gathered for that particular criteria in ventilating under the slab. Whereas if you compare it with what we're doing now, we're actually ventilating underneath the entire footprint of the building, so a complete slab ventilation. So as I say, good bedtime reading, good documents, some of them not quite up to date. The main two documents that people refer to are either the NHBC report or BS 8485 Code of Practice for the design protection measures for methane and carbon dioxide ground gases for new buildings. So those are the main two. The NHBC document works on a traffic light system. So you can see here, green, no guidance, no protection required. Amber 1 would be considered a low level risk. So the introduction of a membrane with a void underneath your slab. Amber 2, elevated level of risk, again, void and a membrane. Red, if you had a red zone, you should consider really having your building actively ventilated rather than passively ventilated. The NHBC tell me that they don't normally actively ventilate underneath their floor slabs, but our system does lend itself to that should you wish to actually do that. The NHBC traffic light system is predominantly for housing applications, so there are obviously only certain floor types that would be suitable or applicable in this particular application. Floor size of up to 150 square meters and story height up to 3 stories. For everything else, for all the other types of building, there is BS 8485. So that will cover all of your types of buildings, from commercial, public, through to an individual house, for example. Those building types are split out from A to D. There is another presentation which goes into more depth than this one, which will outline the different types of buildings and what these letters from A to D actually mean. Simplistically, though, you remember our characteristic gas situation from 1 to 6, 1 being the least severe and 6 being the most severe. Each building type for each particular characteristic gas situation has to achieve a point score. So, for example, a building type B in a CS2 would need to achieve 3.5 points for it to be adequately signed off as protected. So 3 main elements to this. So first of all, there's the structural barrier, which will score you from 0 to 2.5 points, depending on how you build it. Then there is the ventilation protection measure underneath that structural barrier, scoring from 0.5 point to 4 points. Our vent form will give you 1.5 points and be deemed as good under the guidance, or 2 points and be deemed as very good. And then lastly, there is the introduction of the gas membrane or hydrocarbon barrier, scoring 2 points. There has been a change from the 2007 edition of 8485. If you do have any old copies kicking about, it will tell you that your gas membrane or your hydrocarbon barrier will score from 0.5 point to 2 points. That has now gone over to 2 points. So all membranes, 2 points. The venting components themselves, we have 2 different types for passive gas ventilation. So we have a vent form square-legged panel that can be either 80 mil or 100 mil in depth, and will take you from 20 kilonewtons to 50 kilonewtons load that the panel will take. It can be used for either a suspended slab or a ground bearing slab. The vent form cylindrical legged panel on the right hand side there, that is 150 millimeters or 200 millimeters deep, and it will take 9 or 13 kilonewtons load, and it is for use with a suspended slab only. Both panels are molded panels, and they are 1.2 by 1.2 meters in size. If you wanted to ventilate and also guard against heave, we have this product here, which is called Cell Vent HX. It's a combination product. It reverts back to the old model size of 1.2 by 2.4 meters. We have the collection of molded cellular legs at the bottom here, which replicates what our cell core product is doing in terms of protecting against heave. We then have a primary board on the top here with holes in it. So that enables the contaminant to move up from the void below into this area here, which is our maintained void that is kept open, and that is replicating what vent form 8020 will do in terms of dilution and dispersal out to atmosphere. Then we have the top board, which is a 10 millimeter board, nice and strong for you to walk on when you're actually setting out. If you wanted a larger void here, if you had higher concentrations of gases and contaminants you wanted to get rid of, we can actually manufacture that. Okay. The reason this product has come about is really changes in guidance. So if you have an area where you have an expansive clay soil and gas, and you are looking to actually protect your building, the cell core product under heave will compress, and you will have a void that is formed full of spalled material and compressed polystyrene legs. In other areas where heave hasn't occurred, the legs remain upright, and the drainage holes, which are sited at the top of these legs here, provide your cross-flow ventilation. In that scenario, it is simply not enough just to have this layer here. We have to have this maintained open void above it, and hence we've developed this Cell Vent HX product. That gives you an idea of the characteristic gas situations from 1 to 4 and how applicable our vent form system would be to those particular CS situations. Obviously, it has its limitations. If you have a CS4 and you have a building which is 15 meters long on its longest side, that really is your limit for introducing vent form as a passive gas ventilation system underneath the footprint of that slab. Anything larger than that, really you should consider actively ventilating that particular footprint of building. But you can see there your characteristic situation, gas protection guidance value, and the depth of product that we would actually introduce there. For ventilating to atmosphere, there are various different mediums. 9 times out of 10, if we have the conventional envelope setup, so blockwork inner, brickwork outer, air bricks, periscope vent, 2 meter centers. If you can't get it in the wall, we can get it in the floor with either a rectangular or circular gully vent or a rectangular ground gas vent box. Either 5 or 6 meter centers on those. If you wanted to remotely ventilate away from the building, then we would use gas vent bollards, 8 meter centers. It gives you a nice raised up area away from the level of the strata to ventilate out to atmosphere. And you could also use that in areas where you have a high water table. Membrane specification. Simplistically, we have 2 types of membrane. We have a tri-gas membrane, which is suitable for methane, radon, and CO2. And we have a Puriflex membrane, which is a combination membrane in so much that it will take care of methane, radon, CO2, and a range of hydrocarbons. So it is a hydrocarbon gas membrane combined. Membranes come in various different variants, and those different variants will pertain to the different types of membrane that we have. So for example, anything that's installed vertically is always installed in conjunction with a primer and will have an adhesive back to it. Anything that is installed horizontally will normally be loose laid, and the joints will be either taped or welded. If you want to go across a cavity, or if you wanted to extend a membrane underneath a transecting wall that was sitting on top of where the membrane was going to be introduced, we also have a patterned variant. There are various detailing strips, there are various preformed top hat sections. In terms of Puriflex, now Puriflex is our hydrocarbon barrier and gas membrane. We also have modeling software. This is available to use on the website. In terms of specification, it aids the specifier in selecting the correct membrane for the job. So if, for example, you have a particular contaminant on site and you want to know, will Puriflex guard against that particular contaminant, then you can go onto our website, register your interest in so much as your details and also the project and what the contaminant is. Put the information into the system. It will then give you a result reading back as to the suitability of the membrane. So if you know, for example, you have mercury on site and you want to know, will Puriflex guard against mercury, you put all that information in and it will tell you whether it will or whether it won't. And that enables you then to make the choice of is that membrane correct to be specified for that particular application. A lot of contractors over the years I've come across have tried using HDPE as a type of gas membrane. It's not a particularly great solution. Firstly, because you don't get batch continuity, it's a recycled product, so you don't know if what you're putting in at one end of your particular project is the same as what you're putting in at the other end of your particular project. HDPE also lets through a significantly higher concentration of the contaminants than what the Puriflex membrane would. If you're also dealing with VOCs and hydrocarbons, then the type of membrane has to be a fully welded membrane. So those joints have to be welded because there's no such thing on the market as a hydrocarbon resistant tape. So HDPE would predominantly be taped. So as I say, Duraflex, welding it with a continually seamed hot air weld is the only way that you can adequately install that membrane. That concludes our VOC and ground gases part of the presentation. We're now moving on to structural fill. As I mentioned before, all of these fact sheets and information is available on our website. This is looking at our fill core EPS product. So the type of polystyrene that we manufacture at Cordek is construction grade expanded polystyrene. So it is a closed cell product, has good structural properties and some inherent insulation properties. If we go down the side here, we work on a 1% compression figure. So basically we have all these different grades from Fill Core 20 to Fill Core 190. So Fill Core 20 is the lightest grade. So if, for example, we introduce a load of 20 kilonewtons per square meter on a Fill Core 20 at 100 millimeters deep, it will compress by 1% of that 100 millimeter depth. The next line across there is the nominal density. So that is physically what the product weighs in kilograms per cubic meter. That comes in handy when you're actually selecting the size of sheet or block that you would require for a particular application. Fill Core 190, for example, 55 kilograms per cubic meter is a very dense block. So you don't want to be carrying around a 1.2 by 1.2 meter block of that. You would consider to actually have those blocks in 600 or less for manual handling. Thermal conductivity, that is what the product physically is. It is not the U value of the product. Again, if you would like a U value calculation undertaking, we can do that for you. And the same criteria applies as that which we discussed in the expansive clay soils for insulating under the slab using cell core. Maximum depth of concrete, that is simply how much concrete the product will take on top of it for the various different grades. In terms of polystyrene, the actual minimum sheet size is 25 mil thick. It comes in 1.2 by 2.4 on plan, and the block size is 1.2 by 1.2 by 2.4. If you need to go higher than 1.2, then blocks can be easily adhered together. If you have an application like this where we are looking at terracing, then obviously we can profile each one of those areas to suit the terracing above. So this particular example was the Kier Oval, the Peter May stand. This floor slab here actually isn't on the floor. There is another structure underneath it. So we were looking to not introduce any more weight to this particular floor slab, and also to replicate the profiling of the actual terracing. So we always design in two different areas. We design firstly in the temporary state, where we consider how much concrete is going to be put on top of the polystyrene and how it is going to be sited. Is it going to be directly sitting on top of it? Is it going to be spanning on top of the polystyrene? So what are the loads imposed from there? And then we also consider the live load applications afterwards. So what type of loads are likely to be transmitted down through this particular concrete area onto the polystyrene below? We can undertake to offer various different compression calculations to prove that the polystyrene will compress by a certain amount under these particular loads. It comes in particularly handy if you're working with very lightweight screeds and you want to know how much deflection is likely to happen underneath that screed before it's going to cause you a problem. So for example, if you have something like a 65 millimeter fiber reinforced screed, and your screed manufacturer says, right, okay, well, we can accept 1 millimeter of deflection in that before we have issues with the actual screed cracking, then we need to make sure as a manufacturer we are specifying a grade of polystyrene to sit underneath that screed that is robust enough to hold that screed up underneath that particular load and stop that from happening. The load calculations, we can do either a UDL load calculation, we can do a point load or a linear load calculation. Again, that's all emailable to you or your client for their paperwork. So all of those are available. Looking at another application here, this was a London Bridge Station redevelopment. So essentially this was a project right in the centre of London. It was a live railway station with some historical arches that had been introduced during the station's primary construction, and this particular new station was being introduced on top of those arches, so obviously they were quite load sensitive. The client was quite keen to use polystyrene from an environmental point of view, simply because if you consider having conventional fill on 8-wheel tippers going through centre of town to get it to where it needs to go, there's quite a few cycles of those particular vehicles taking your material into the place where it needs to go on site. Polystyrene, however, you can get a large cubage of polystyrene onto very few lorries and into where it needs to go. We also had different grades selected for different areas of the actual station itself. So underneath the track, we used a higher grade than areas in between the track. This particular area here, the distance between the arches and where the actual top level of the track was between 3.5 and 4.5 meters. So quite a bit of polystyrene being introduced there. In other areas around the station concourse, underneath the actual stairs themselves, we used again another lighter grade. Both applications were used in terms of standard products, so blocks and sheets, and also what we call a cut to fit solution. So cut to fit solutions basically was where we were making the actual polystyrene suit a particular site dimension. So if you have underneath the stairway, for example, a triangular shaped piece of polystyrene that you want to introduce underneath there, we can cut that and manufacture that before it goes out to site from Cordek. When it gets to site, again, each of the pieces are all labelled up. They're simply introduced where they need to go. Again, as it was a railway station, we may have historic views of hydrocarbons on site. So, you know, that could be either from spills, historic spills from railway locomotives, heavy oil that's on site in the strata below, and also we wanted to guard against new spills from traffic above. So indeed, when we put the polystyrene blocks on site, introduced those, you can see there we also used our Puriflex membrane to guard against any hydrocarbons and contaminants that might be there that are going to come into contact with the polystyrene. Polystyrene will never be cheaper than conventional fill materials. The reason that people select polystyrene is for its intrinsic insulation values, the fact that it is very adept to profiling, shaping, routing, reduction in cycles of getting the material to site, so reduction in the environmental impact, and also on load saving towards load sensitive structures that may be underneath. If you are considering doing something out of the norm with polystyrene in terms of either shaping or routing, then this is where we come in with our project support service. So at Cordek, there are various different ways that we can actually take our block and sheet and produce it into the products that go out to site. We can either use molding, we can use 3-axis or 5-axis hot wire cutting, or we can use 5-axis CNC controlled routing technology. So essentially, we will advise you with our construction engineering expertise in terms of what type of block you could consider, block size, block density, design guidance, perhaps do some compression calculations for you there, and then we can agree on having a set of drawings that are issued, and from those drawings we can then build up our CAD/CAM package on that and produce a precision model from those drawings that can be then 5-axis CNC machine routed to go out to site. So if you need to consider things like a waterproofing layer, various finishes, primers, gel coats, GRP layers, all of that can be put into the mix and given to your client, so we can provide a total solution to what might be perhaps quite a complex shape that they would need to have on site. Finally, and thank you all very much for listening, just a little bit about our support services. If you do go on our website, we do have a technical library with our product range contained within it. We also have our data sheets. We're a member of the National BIM Library. We have various technical standard details. You know, if you have a particular site application and you'd like to introduce one of our standard details, they are there. If you can't see what you want, please do ask us and we'll be happy to draw you one up. In terms of what I actually do, help with writing specifications for your clients, assistance with non-standard requirements, as I discussed before, anything that you might consider a pattern or a mold or a separation layer or GRP, happy to discuss that. Site visits, we are able to visit site either on your behalf or to assist the contractor with installation of our products, and we do have a technical support team. We're based in Slinfold in West Sussex. We cover all of the UK, Northern and Southern Ireland and the Channel Islands, and we do offer export as well. So if you would like further information on any of the other CPDs that we do, please do get in touch. There are some more product specific ones. My thanks again for everybody listening in, and I will now hand back to Jordan. Thank you.
Thank you, Simon. Okay, so in terms of questions, we haven't actually had any come through, so I'm taking that as a very positive sign that you were just very thorough with your presentation. So I will just say a couple of things then before closing off. So of course, a thank you to Simon for presenting this morning, and thank you to everyone who has logged on and watched the presentation. If you have any feedback, please do send it through to me and I will share it with Simon outside of the session. Our next webinar is on the 18th of November at 10 AM, and this will be covering sustainable user innovation in residential homes with Liz Berger. So again, any feedback, comments, ideas for future webinars or anything else, please email me. You can email the webinar's email address or just send them through directly to myself. I hope you all found it very informative this morning. Thank you again, Simon, and I'll hopefully see you all online again soon.